Okay. Good evening and good morning, everyone. Welcome to today's webinar. My name is Fang Fang. I'm VP Events for Alberta AI Association. It's my pleasure to be hosting the webinar given by Mr. Bruce Matichak today. So for those of the audience who regularly attend our event, you already know this event is held monthly, aiming to sharing the research achievements and advances of AI technology contributed by the speakers and their work. And this event is co-organized by CNKI China and Alberta AI. If you would like to know more information about AI events and programs organized by Alberta AI, please visit our website, albertaai.org. So now, next, please let me introduce today's speaker, Mr. Bruce Matichak. Mr. Matichak is the co-founder and CTO of HealthGauge, which is an Edmonton-based company building a health information platform. Bruce has a master's degree in computing science from the University of Alberta and has worked as the CTO for several AI-based companies, startup developing intelligent systems. His products were deployed at several Fortune 500 companies, including IBM, Apple, Lockheed Martin, Liberty Mutual Insurance Corporation, United Airlines, Hallmark, and others. Applications Bruce has developed include secure email, image recognition, behavior recognition, machine learning-based biosignal estimation, remote patient monitoring, telehealth, and conversational agents. So today, Bruce will give a talk about an approach he developed addressing bias and error in neural networks. The next lecture will take 1 hour, first about 45 minutes speech, and then following by 15 minutes question and answer session. So the audience, you can ask questions under discussion section, either during the presentation or after, and then Bruce will answer the questions after the speech. So now let's welcome Mr. Bruce Matichak to give his presentation. So Bruce, go ahead, please.
Okay, well, great. Thank you very much for the opportunity to present. So we're going to look at some of the things that we're doing at HealthGauge to use neural nets to do something called blood pressure estimation. And we're just going to look at some of the issues that we encountered as we built neural networks for blood pressure estimation. So I'm a startup entrepreneur. I've worked on a variety of commercial products. As you heard, I have a master's degree, and recently I decided to go back and finish my PhD. So hopefully I'm going to finish that work, and I'm working in the area called neurosymbolic computing. So if any of you are interested in those topics, I'd love to hear from you. A lot of the work core work that I'm going to be talking about is actually done by Juan. So Juan Diego Castro Miyashiro is a programming genius who works for me, and he's done a lot of really great work on HealthGauge. And so Juan, if you want to interject and correct me at any point in time, please do so. But again, thank you, Juan, for all the great work that you've done. So the key issues that really we're dealing with here are that some mean absolute error can be misleading when you're actually working on neural nets. And we'll talk about that. We'll talk about the data. There's some errors in the data, and the errors come from people and they come from measurement. Lots of errors can occur. The data also has kind of a natural bias, right? Which is, so if you're, whatever you're measuring, whatever you have the most measurements of, that's where your data is, that's where your estimates tend to be biased towards. So we want to talk about some of the ways that you can correct that bias. And then there's some more advanced techniques, something called contrastive loss. We'll talk about that to address some of these errors. So our approach, upsampling can address bias, label distribution, smoothing, which is a way to re-weight the loss functions. We'll talk about that. We'll talk about what we mean by contrastive ensembles. So these are kinds of neural net ensembles that can look at noise and improve accuracy, and a specific kind of ensemble, which is this based off of the twin networks idea. We'll talk about that and how we've used that to good effect. So let me just talk a little bit about what we do with HealthGate. You can see I'm wearing a little device, and that device looks like the device in this picture. This device takes a whole bunch of data, electrocardiogram data, photoplethysmogram data, which is the little light, that shines into your wrist and measures the blood pulsing in your wrist. And we take all that data plus some demographic data, and we run that through a neural net in order to estimate blood pressure. So this is actually a picture from our application. If you open up HealthGauge, you can see all the different readings that we capture, but that big button in the middle, you click on that, and that takes you to an area where you can actually read it, read the blood pressure. Now, the thing is, we want that to be accurate as we can possibly make it. So, but the goal is not to use a blood pressure cuff. So if you look at a blood pressure cuff, it kind of squeezes your arm, kind of painful, it's inconvenient, but this is how a blood pressure cuff works. Basically, a blood pressure cuff, you inflate this cuff, it squeezes the blood until the blood literally stops pumping in your arm, and the amount of pressure required to get to that point pushes mercury up into a column, and the amount of mercury and the level that gets that it gets pushed to is what's known as the your blood pressure reading. And there's two levels. There's the systolic level and the diastolic level. The systolic level is the level where you start deflating that pressure, and then you can actually hear the blood pumping now, and then you continue to deflate until you can actually it's smooth, and that's called your diastolic level. So you get these two readings. So if most doctors they kind of look at the systolic level and they want to know, well, what is that prediction? And so we did a whole bunch of work, and we came up with this mean average estimate of 4.9 milligrams. So this is super accurate. This actually, this is as accurate as any FDA approved blood pressure device on the market, but there was some problems with it. And the problem had to do with bias and error. So when we took some measurements, what you can see with these measurements is whenever they're over a certain value, it was underestimating the blood pressure. Okay, so we have a data bias problem. So when you look at empirically, when we take all of these readings, you can see that a lot of the readings are clustered around 120. Well, why? Because that's a normal blood pressure, right? So normal blood pressure is 120 over 80. Most people that are normal are going to have that. Some people lower, some people higher, but as you age, it kind of goes up. And so this is why people want to be able to keep track of their blood pressure. But what you can see is that the error in our in our data corresponds to the balance, if you like, of the readings. And so the graph on the right shows you what the error bars look like and what the estimates are. So we're significantly underestimating as we get to larger areas, so larger blood pressure values. Okay, so how do we fix that problem? So we've got a bad data problem. There's a couple of places where data is bad. So we have a bias problem. So now let's talk about bad data. So users enter wrong data. It's just wrong. Like they just type the values in wrong when we're generating these training records. What's happening to get these training records, they're actually putting on a automated what's called an automated oscillometric device. That's what you see here. And, and it comes out with these readings. You can see the systolic at the top and the diastolic, and then your heart rate. And you take those readings and you can enter them into our application and then save record. But there's also noise introduced by the equipment because the equipment itself has error when you're measuring. So you've got lots of places with error. Well, normally with machine learning, one of the ways that you correct errors, you just take lots and lots of readings. But what happens if you don't have enough readings to really correct for all the error? So this is where you need these, special techniques to address error. So what can we do to address the data imbalance and the error problem? And this is a regression task. So we're looking at some continuous value going from 20 or whatever all the way up to 180 or higher. So the first thing that we can look at is something that we call label distribution smoothing, which is some work by Yang et al. And what we do is, first of all, we look at the empirical label distribution. So where are all these output labels being distributed to? When we develop this estimation capability to estimate what the distribution is. And so then what we're going to do is we're going to modify our loss function to use a weighted loss. And the loss, so every time we take a reading and we're recording a reading, we basically weight the loss, and the loss is going to be inversely proportional to the estimated distribution. So if there's, if there is, so that's basically what you do with the smoothing. So then this kind of smooths out all of the values, and it can basically addresses the data rebalancing. So now the other way that we can address rebalancing, of course, is we can look for bad data. We can take out bad data, relabel it. But the other thing that we can do is upsampling and downsampling. So, or you could call it resampling if you want. And so one of the ways that we can upsample is we can generate data. So one of the techniques that we looked at was using the generative adversarial networks. This is a great way to simulate data, and how this works. So this is an example of our network. And if you looked at GAN and how GAN works, with GAN, what you build is you build a generator, and the generator actually generates data. You give it examples of what looks like good data. And what we do is we introduce a training vector into the GAN network so that we can give it arbitrary values. We can give it a blood pressure value, and it will, based on the value that we input, it will generate a synthetic set of signals for us. And then we can take those synthetic signals and run them through and use them to generate training data. And so this works pretty good. We use that to some effect. The other thing that we can use is we can look at the sampling rate. So synthetic data can increase your samples. Sampling rate, when you look at the stream of data coming off of the wrist, you've got a PPG signal, you've got an ECG signal. I'll show you what those look like in a second, but it's the stream of data. You take about a minute's worth of data. What you want is you just want to sample window size in order to record a particular blood pressure record. And you can make that window wider or smaller. If you're looking at a particular range of value and you're going, okay, well, I've got lots of data in that range already, I don't need more data in that range. What you can do when you're saving that training record, you can divide up the reading into a bunch of windows, and you can have larger windows, which basically mean you get more accurate readings per window, but you have fewer records, training records that you generate for like a 1 minute signal. And so doing this dynamically allows you to generate, to modify your sampling rate and therefore get more or less samples in certain ranges of data, which can significantly help you with your bias. So the other thing that we looked at in order to increase the accuracy of the data is we looked at something called contrastive loss. So contrastive loss is a really interesting way to look at your data. So here's an example using faces. To a contrastive loss network looks at pairs, and what it does is it takes pairs that are similar, and in the semantic space prior to your decision-making layer, in that semantic space, it brings those points together, right? You can think of it as pushing those points together. And then in the semantic space where those images are distinct, right, it pushes them apart. They get in semantic space, so they pushed away. And so because and what this allows you to do is it increases the intelligence of the semantic space, because you have clearly defined categories. And we'll see what that looks like in a second. So again, just to reiterate, we're doing contrastive loss. We're taking all of our data points and we're pushing, and ones that are close, we're pushing together in semantic space. So if you think about in blood pressure, if the blood pressure values are close, we want them to be grouped together. If the blood pressure values are far away, well, then we want, in semantic space, we want the decision making to be, to be much farther apart. So, so here's an example. It's, faces are a little bit complicated. Blood pressure is really complicated. So just to illustrate the point, we're looking at icons or handwritten characters from the MNIST database. And so using this concept of contrastive loss, you can train a neural net so that the icons, or the numbers, the digits, get positioned in different parts of semantic space. And this is really interesting because you realize that semantic space, each concept is a contour, it's a shape in semantic space, and you can mold that space in whatever way you want just by training your loss function. And in this particular case, when we train our loss function, you end up with these really, really precise clusters. And so this image actually comes from triplet loss TensorFlow training. So this is Google's TensorFlow training for the triplet loss function. And you can see everything goes into these nice categories, but some interesting ideas here. First of all of these categories are equidistant apart. There's no structural construct that tells you in semantic space this category is really close to or far to the other one. Like look at 1 and 3 and 4, they're all equidistant from each other. Whereas really, I mean, 4 is a long way from 1, much farther away than 1 is, if you think about numerical separation. But yet in the semantic space, they're all equidistant because that's all that the loss function is considering. So what we want to do, though, is we want to adapt this idea to regression, right? And so we want to use and with regression, what we have is we have a continuous set of values, and we're trying to estimate blood pressure, on this continuous line. And so discrete classification is not as valuable. And so what we decided to do is adapt the triplet loss for regression. So this is based on work by Wetzel and company. And they, this is out of Waterloo, and they came up with the twin regression idea. So we looked at adapting it to work with blood pressure. And so this is, that was the approach that we took. So let me just talk a little bit about building a network using the distance semantic, right? So, so you wanted to make this work. What we want to do is train a neural net to find a function. And the function that we're trying to learn is the difference between 2 points. So, so we're not training the network to learn individual records. If you think about blood pressure, let's say you take a reading, I take my reading, I get it out of the watch, and then I get a reading of, and I get a whole bag of data coming off of the watch. So now what I want to do is I want to estimate. I actually don't, with this particular technique, I'm not actually using the value of that reading to train the network. I'm using the difference of that reading to some other point, and I'm training the neural net to generate a difference function. So that means that if I have I generate many more data points. So if I have 100 records, well, now it's like 10,000 data points. If I have 1,000, well, that's 1,000,000 records now. So I have 1,000 records, I can generate 1,000,000 training values, if you like. And this ends up training, doing a really good job of training this this distance function. And so again, the X's correspond to the biosignals and the demographic input information, and the Y's correspond to the difference in the blood pressure. All right, so let's talk about how the training actually works for this difference function. So what we do is we start with signal 1, and then we have some other signal 2. What we do is we know what in the training record is telling us, oh, this is one value reading, so this is a 100, and the other signal is going to be 110, and so we then train the difference is 10, and so that's what this network does. So this is a twin network. You can see it's got like two legs, if you like, that are inputting it, but it's outputting a difference, and that's what we're learning. So it considers the pairs plus the demographics, and then we're predicting the difference in these values. All right. So now, once we're all done, and we have a great way to take any 2 points of readings and any 2 readings, and we're able to estimate the difference, how do we use that network to actually generate a reading? So this is how we do it. We generate sets of anchor points, and the anchor points are a set of readings that we're really confident represent the that are really good values. We've done as much work as we can to determine that these are the good values. So here's how the anchor set construction works. If you take any let's look at just 3 points and take any 3 points. So if you take 100, 200, 300, the average difference between any 3 points is going to be 0, right? So the average value between a set of consistent points is 0. So if you get 3 points, so let's say you take three points, and you actually use this neural net, this twin neural net, to give you a difference between these points, and you take that average difference. If it's not 0, that means that those points aren't agreeing, right? There's a disagreement. And so let's just say you've got two really, really good points, and you take a third point and you run it, and the difference between those three is really low. Well, if the difference is really low, well, then you can add that point into your anchor set because you know that you got a good point. But if the difference is really high, well, then it's probably not a good representation of, of the function, of the difference function. And so you want to exclude that from your anchor set. So you can use this technique to generate a really rock solid anchor set. So now that you have an anchor set, how do you actually use that anchor set to make a prediction? So here's what you do. You take a set of anchor points, and it doesn't matter what the values are. You just know that you've got a set of anchor points that are good. And then you take this test signal, and what you do is find the average difference between those anchor points and this new value. And that average difference is going to be the actual predicted value. So let's go through an example. So let's just say I've got an anchor point, and the anchor point blood pressure is 90, and then I've got another one that's 100, and then I've got another one that's 140. Well, what's going to happen is I've got some unknown test point, and I don't know what the difference is with this, with this test point, right? So what I do is I look at the first difference, and the first difference says plus 10. Well, and then I look at the next one, and the next difference is 0. And then I look at the last one, and that difference is minus 40. Well, the average estimate here is 100, and that becomes the estimate for this data point. And so using this technique, what you have is you have an ensemble, right? So here's kind of the simple mathematical equation that, that represents this ensemble-based contrastive prediction technique. All right, so now we know how to generate points. Here's something really, really interesting when you apply this technique to the MNIST data set, right? Remember what we had before. This is what we had when we segmented everything according to, when we segment them according to just the categories. But now when we do regression-based segmentation, we end up with this really interesting space. Each one of those estimates is now, and if we continued to do training, we'd probably end up with deeper clusters. But the fact is that those points that are farther away from the center point, those points are probably farther away because there's, possibly error in the labeling. Maybe there's a lot of ambiguity, but, a 1 doesn't always look like a 1. A 1 can sometimes look like a 7, depending on how elongated, say, that top line is, right? And so there's a little bit of differences between them, but numerically, those digits go from 0 to 9. And when you array them in semantic space using this particular technique, you end up with this really, really great segmentation. So I think this is just a fabulous illustration of the ability to shape semantic space according to a particular semantic. And so again, this is a reminder of what that looked like when we were just doing this categorical separation. So putting this all together, right, into one big, into one big network, this is what the prediction error looks like in using using our data, and you can see it's significantly improved. And so it's significant, it's improved to the point where this is, functional as an FDA approved device, which is what we're trying to do with our device. All right, and so that brings me to the end of the talk. So the talk part, so hopefully we have some questions from people. So this is my contact information if people are interested. And so I'll just open it up for questions.
Okay, thank you very much, Bruce. It's very interesting topic, and it also goes so fast. Yeah, so your presentation just finished in less than 30 minutes. So the audience, we have 30 minutes to ask the questions. If you do have a lot of questions, you have time. So let's see, do we have any questions coming? So I would like to ask questions for the neural network. We know NN is a very powerful tool in artificial intelligence, the technologies. So what's your the major challenge when you develop this approach for your topic? It's yeah.
Yeah, so you know, when you're building a neural net, there's so many different structures that you could choose from. And so how do you pick the best structure? How do you decide which features are in, which features are out? You know, that has a lot to do with how you're structuring data. So in our particular case, you know, we have ECG data, we have PPG data, we also have demographic data. And originally, when we were looking at this, you know, the neural net, we decided to build feature detectors. So we looked at the features of the ECG and the features of the PPG, and we built pre-computing into the architecture. And we would pre-compute where, you know, where rises were and drops were, and you know, the widths of certain curves along the way. And it turned out that this was unnecessary, because if you just put the whole raw signal into the CNN, the convolutional neural network, the convolutional neural network builds detectors that figure all that out for you. So you don't have to do all of that feature work. You just have to have enough data that the network can you know, can build those features for you. So when we you know, so our network kind of consists of this convolutional neural network with these signals as inputs, and then we just have a sort of a final dense layer looking at some demographic information, and you know, altogether it forms a, you know, pretty accurate estimation, particularly now that you've got this loss function. So the other thing that we have done to correct problems, so as I pointed out, the big problem is we don't have a lot of data, and that's a huge problem. And we don't have we don't have a lot of data, and there's a lot of errors in the data. So we have to correct for, you know, for those errors. So one of the techniques that we looked at was just ensembles in general. So just building an ensemble, typical ensemble technique where you build multiple versions of the network by selecting different data sets. And that worked, you know, it actually helped, you know, it was a pretty good technique. But this other ensemble technique using contrastive loss actually does a better job. And so, you know, so we're experimenting, you know, continue to experiment with that. So one of the other things, of course, is when you're dealing with low levels of data, not very much data, the other thing that we did, you know, we tried to use upsampling. So we actually looked at a few different upsampling techniques. One upsampling technique was based on you know, was based on GANs. So I talked a little bit about the GAN approach, and that's kind of a really interesting idea, because the synthetic data allows the neural net to explore a semantic space where you might not have enough data. We also looked at SMOTE, which is another. So sorry, that's my dog entering the house. So we also looked at SMOTE, and SMOTE is a really interesting idea because it's a upsampling technique where when you have trained data points that, you have some points that are trained and that these are really, really good points that are very indicative of, of how the network should work, you can interpolate between these points. And any interpolation between these points is a new point. And you can use that new point to train the network. So you interpolate, the output and the input between these 2 points. And so SMOTE is a really good way to generate. So we experiment with that, and that actually works fairly well. I mean, and the other technique that we are experimenting is, I would call it feature generation. So if you just take a point that is really, really good, you can generate a lot of additional points based off of that point just by, if you like, randomizing the input features a little bit. So you just add a little bit of Gaussian noise to all of your input features, and you can generate a whole bunch of new data, right around that point, because because there's so much inaccuracy when you're taking these readings that that a little bit of error is fine. And so you just can generate a whole bunch of extra points, and that actually works fairly well. So so those are the problems with with building the neural net. I mean, so I guess we could talk about some of the other issues. All right, so we could talk about some of the other problems with generating or some of the other tools that we used. But anyways, maybe I'll just stop there, and maybe people have some other questions.
Okay, so I think because you are analyzing the the data from health system, right? So is it possible right now, for nowadays, you can get the data from the hospital or for are they accessible? Just
well, not in Canada or the US anyways. There's a lot of issues basically that you have to resolve when you're collecting data from people, right? You have to have so ethics committees and whatever, and you're not going to get the data without getting people's permission. You could just get data, like if it's just private, you can get people's data. So if you have a bunch of devices and you've distributed them to your friends or whatever, you can get that data. But when you go into kind of a public setting, it's very problematic. And the hospitals have this data, but they don't want to release it to businesses. And even for university researchers, it's a huge process. So I work with a few other people from in the province, right? And we're talking to Alberta Health Systems. One of the things that we're looking at is a de-identification mechanism using what's called federated learning. So if you ever heard of this concept, federated learning is really a really interesting idea, where what you do is you divide up your neural net into 2 halves, if you like. Half of it is actually sitting on the source computer, but the other half is actually sitting in a training system. And so the top half of the network, once your data goes through like one layer, it's de-identified. So you can you can then send that data off to your second half sitting on your server. And using this federated technique, people have, people have gotten past some of these identification problems that exist with data. So the big problem you have is de-identification of the data. You have ethical problems with running studies, collecting the data. So working with health is tough.
Yeah, I know. Since usually the data sets, the number of data sets is usually a problem to be applied to artificial intelligence, because it really need a big data. So I think for developing a model or using data we can simulate, right? We can use the simulation approach or interpolation. But the thing is that how do we validate it if we do not have real data?
Well, you have to have some real data, right? So
yeah.
So you find a few people. I mean, this is the approach that we took. We found a few people that are in agreement, right? Friends and family and employees and whatever. And they generate enough data that you can start doing simulations. So when your simulations start being highly reflective of actual real data, then you know that your simulation is working. You can then start doing interpolation, and you can interpolate using GAN techniques, which are just one way to simulate data, or SMOTE, which is just another technique, or other tools, right? I mean, and these techniques, they work really well. I mean, at some point, if you have a technique and you want to go to get FDA approval, you have to do a clinical trial, and you're not going to be able to you just have to do a clinical trial. But it doesn't really matter how you develop your neural net at that point. The only thing that FDA really cares about is whether or not your device works, right? So that's an approach that you can take.
Yeah. Anyway, so I do see your approach really works. You give a really good results. So hopefully, giving the more data, your approach, your products can be someday commercially to be used to our health system. So thank you very much for neural networks. I do because my research is really mainly focused on the neural networks.
What area
I'm working on to analyzing the wind turbine.
Wind turbines.
Yeah, wind turbine. To try to using the artificial intelligence technologies to predict the failure, very accurately.
And what data are you bringing in when you're looking at a wind turbine? Sound data, vibration data?
Vibration, yeah. Because we mainly focus on analyzing the rotating machine, like a bearing in a gearbox.
Is there a commercial application, or are you just doing this for research?
Research, but we do develop some prototype. Yeah, try to collaborate with the industries. It works well.
Yeah, well, I guess the problem with looking at failure, right, is you're not going to get much data, right? Because it has to fail in order to.
The thing is that we do have a bunch of data, but like what you said, there's a lot of data quality is so bad because they are working in a very noisy environment. So we need to identify the good data. We need to to try to figure out what data we need to have, which are necessarily to use the neural network to give the good results. And also we need dimension reduction technologies. Otherwise, our models will really time consuming. So efficiency is also our topic, within this area.
Yeah, I mean, the thing about dimension reduction is you don't necessarily need to do dimension reduction at the input layer, because the neural net will just tell you the dimensions, that you need.
Yeah.
Like the other thing that you can use, like, to analyze these, the semantic space, is variational autoencoder. I don't know if you've tried those, but variational autoencoder is really interesting because you can squeeze the dimensions down to whatever you want, and if the signal is present at that semantic layer, then the decoder part of the variational autoencoder will be able to regenerate the original signal, right? So this is the cool thing about the variational autoencoder concept, right? And so then what you can do is then explore that semantic space to see, does it represent the information that we need to extract, and it doesn't really matter like how what your input is, because the encoder just encodes down into a small set of values. I mean, are you guys looking at that kind of technique, or how do you explore the semantic space?
Our common approach is that, before the neural network, we take a lot of data, but we need to, extract the good features and the sufficient features. For those of the features extraction, so we need to, using some decoder or using some dimension reduction technologies, and then determine which features we are interested in, and then go to the input of the neural network. And also there's a lot of things to do to to find a good structure of a neural network. Yeah, we can talk about later. So I think that there's a really lot of interesting within the artificial intelligence this area, because for any kind of applications, I think the technologies or the approaches, there are always much similar. We just use some of the data analyzing data scientists.
Yeah. Well, there's some also in the newer techniques. So one thing I would say is, you don't have to work that hard to do feature analysis, because if you have a really good neural net, it will build the features for you. So
yeah, that's right. Yeah, I agree with that.
Just let the convolutional neural net find your features. There's also another really, really interesting idea emerging, and you may have saw this paper, Attention is All You Need. Attention networks are another way to do the same things that neural nets do. I mean, they're a kind of neural net, but the way that they process the semantics is different, because each layer looks at all parts of the layer, and then you go to the next layer, and then that layer looks at all parts of the layer, and you end up with this semantic, you end up building these higher and higher levels of semantics. So that's what the transformer network does. And so that is a really, really, I think, interesting innovation that's going to change, that's going to have a big influence, because maybe you don't need CNNs. Like, maybe transformer networks are better. And the other thing about transformer networks is that they seem to process each layer better, because there's on these modern day GPUs, there's some operations that seem to do matrix operations that are highly optimized towards these attention mechanisms. So so that's I think one thing that's really going to change. And within a transformer network, you look at all of the CNN kinds of architectures that are out there, and different ways that you have layers and encoding, and all of the work that you do. And so, of course, AutoML and various hyperparameter tuning techniques that are available to you, well, you don't care about any of that with a transformer network, kind of all goes away. So I think that this is a really interesting idea, and maybe something that, and if you want me to do another talk on that, then maybe I'll come back and do a talk on
That's very nice. Yeah, we do. Yeah, we do have some, group mates. They are working on some transformer networks. So I hope we can have some time to discuss about that with you, if you if you are free to discuss with us.
Yeah.
That will be very.
We haven't started. Yeah, we didn't start yet. Like we haven't done attention yet with these signals, but that's next. So this is a set of research that I'm starting right now, which is the application of attention networks to the same signal analysis, and see if we can get better results.
Okay. Yeah. Let's keep keep in touch for about our research. I think that will be contribute a lot, for our maybe future products.
For sure.
Yeah, sure.
I mean, well, I was just going to say we got like whatever. I'll just mention one other thing, and that is the introduction of logic. I don't know. Have you looked at the introduction of logic into the neural network?
Not yet. So
yeah. So this is this new field called neurosymbolic computing.
Okay, we'll make some notes. So logic, introduction of logics.
Yes, introduction. So have a look at neurosymbolic computing, because in some cases, if you can extract some symbolic representation of your problem, rather than using a neural net to come up with a final solution, you can convert your problem into a symbolic problem and use constraint reasoning or some other reasoning technique on the end results. And so this is, I think, going to be another huge direction in machine learning over the next few years.
Yeah, thank you very much for this information. I will do some study on that. So there's another questions coming. So the audience asks, what other products are your company developing using deep learning techniques? Other products?
Well, that's a great question. I love that question. We're working on evaluating the life journey that a person has as you track data. So just to give you an example, I'm wearing this thing, and you also have diabetes. Well, if your doctor is looking at your data, they should be able to see that if you don't have high levels of activity, your glucose levels are going to go up, right? And so the ability to monitor a person's data over time and be able to estimate the trend of that data is a really interesting field inside of digital health. And this is where we're applying neural networks. So we want to be able to take a person's data over periods of time and be able to say, okay, your condition is improving, your condition is critical, and then ultimately even be able to make suggestions to the person. You need to get more sleep, or you should have higher levels of activity based on the trend of that data over time. Because our device, we capture not only blood pressure, we capture sleep, we capture heart rate variability, activity levels, so number of steps, etc. So we can use that data. And so this is another area of the application of neural nets and AI that's important to us. Another area that we're working on is conversational computing. So when people go to use these systems, they have to be able to interact with these systems. And sometimes people are elderly, they don't want to actually click and drag and use GUI interfaces, but people can talk, everybody can talk, right? And so so we're looking at neural networks, GPT-3, other large language models, the integration of neural networks with logic to be able to help people use our system. So, you know, you can use it to help you navigate. You can use it to tag your information. There's a lot of applications for these conversational systems and they've gotten really, really good. So if you look at GPT-3 right now, it's such a fascinating tool. So that's the other area. The other thing that we're doing inside of HealthGauge is, you know, we're working with other companies to look at other kinds of problems. So we're looking at non-invasive blood glucose as an example, and the application of neural nets to that. We're looking at alcohol or lactose or any kind of problem where you can, you know, take a reading off a person's body and just have a signal and then run a neural net through that signal. Those are all prime candidates. We're also opening up we're also doing a bunch of work on the heart. And so if you look at that single lead ECG, so off of this thing, we get a great ECG signal, single lead ECG signal. It's got a whole bunch of information in it. Well, you can predict AFib, afibrillation. You can predict, there's about 10 different cardiac conditions that you can diagnose just by looking at that. And so with enough data, we can apply neural nets to that problem. So, so those are just a few areas. Stress is a really interesting area. We actually came up with a way to detect COVID using just that. All you need is signals coming off of that, and we can detect COVID 7 days in advance of you actually having symptoms. So there's so much data coming off of this wearable. There's so much that you can do. You just need a good neural net.
Oh, wow. So that's so amazing. I think those are really, really good idea and good plans. So you must be hiring people. A lot of work to do.
Yeah, for sure. Send me a resume.
Okay, so please, if you are interested in the Bruce company, just go send your resume. Yeah, they do have really good products plans, I think. Yeah. So I think there's already 7:57, almost 8. So if you do not have more questions coming, then we can conclude today's webinar.
Perfect.
All right. Okay, thank you very much, Bruce. I hope you can give another presentation in some future days because they are really interesting.
Okay, well, thank you very much.
Okay, so thank you very much, and Bruce, for bringing such an interesting presentation. So I think we have no time to do more questions. So you are encouraged to get in touch with Bruce because Bruce has already showing his contact information.
Yeah.
Oh,
so
okay. Screen is off. Okay. Okay, thank you very much, Bruce, for today's impressive presentation. Thank you, everyone who attended the meeting. Time to say goodbye, and you are free to get in touch, contact Mr. Bruce Matichak and also Alberta AI if you do have any questions. All right, let's see next month. Bye-bye, everyone. Bye-bye, Bruce.
Thank you. Bye now.
Bye.所以就结束了哈。